Hi! In this video we're going to introduce the Cauchy integral formula and some of the many consequences that follow from it. It's a very useful theorem, both conceptually and theoretically as we go ahead and prove later results, and also as we evaluate some integrals, as we've been doing in the past sections. Here's what the theorem itself says. Let's suppose that f is an analytic function defined on a simply connected domain D. And let's suppose that C is a simple closed contour that's completely contained in D. Then for any point z0 that is enclosed by the contour C, f of z0 is going to equal 1 over 2 pi I times this integral around C of f of z divided by z minus z0. Now, as we've done in the previous statement of the Cauchy-Goursat theorem, we can get away from talking about the simply connected domain D if we just rephrase it and say, if f is analytic at all points within and on a simple closed contour C, and z0 is any point enclosed by the contour C, then the integral formula we stated above holds. All right, now it may take a little bit of time to digest what's going on here. You may wonder, where did this integrand come from? Why do we have the function divided by z minus z0? But we'll see some implications of this, and maybe you'll get an idea of why this is such an important theorem. Now, our first implications we're going to mention have to do with evaluating integrals. Now, we've been doing this a little bit. We saw how to do this the brute force way using parameterization and plugging and chugging. We looked at the Cauchy-Goursat theorem, which showed us that certain integrals were equal to 0. And in fact, that's where we'll start here. Let's suppose that f and z0 are as in the hypothesis of the theorem. So f is analytic within and on the curve C. z0 is enclosed by C. As we mentioned, the Cauchy-Goursat theorem tells us something useful. It says that if we were to just integrate the function f of z along that contour, we'd get 0. Now on the other hand, if we were to take the fraction 1 over z minus z0 and integrate that around C, we know from our rule in the previous section of the text that this integral will be 2 pi I, no matter what the contour C is, as long as it encloses that point z0. Now the Cauchy integral formula is kind of a mixture of both of these integrands. We're going to take f of z, divide by z minus z0, and the formula tells us that the answer to this should be 2 pi I times f of z0. Now right away you can just see that if f of z were the constant function 1, then the Cauchy integral formula gives us this rule that we've been looking at lately. But it's going to be a lot more versatile than that. In a minute we'll see an example where we can actually use this to evaluate an integral very simply without having to do any real work. Now that's a practical implication of the Cauchy integral formula. Here's one that's a bit more theoretical. We know that f of z0 is equal to 1 over 2 pi I times this integral if we satisfy the conditions of the theorem. Now as you take a closer look at the parts of this formula, keep in mind that z0 is any point enclosed by C. And this value is the integral is evaluated along the contour C. And so what we're saying is that on the left-hand side we have a value of f at a point z0 inside C. Now on the right we have an integral that just deals with values of f at points along the boundary curve. Right? If you went back to the definition of the integral, you'll see that we're just taking a limit of Riemann sums, in effect, where the values we're evaluating at, the function at, all come from the boundary C. So in a sense, the value of the function inside the bounding curve is completely determined by the values of the boundary curve, the values of f along that boundary curve. Now, conceptually, we can think of this as being, or we can distinguish this from what happens with a trampoline. So let's imagine that you have a trampoline, and for the sake of our example, let's suppose that the edges of the trampoline are entirely securely fastened to the end. They don't really move around as you jump on the trampoline. Now, the value, if we take height as our function, the value of that height function along the boundary is sort of not completely determining or determined by the height of the trampoline in the middle. That height in the middle can move up or down while the boundary values of height stay the same. But that's not what happens with analytic functions. What we're saying is that once you know what the function is at each point along the boundary, if you plug it into this formula, it's going to tell you what the value of the function is at any point inside. So for instance, if I wanted to know what the value of f of 1 is, and 1 was inside my curve and I knew what the function values were at 1, all I have to do is plug in those function values, take z minus 1 as my denominator inside those Riemann sums, put it all together, and that computes for me f of 1. If I wanted to find f of 2, and 2 is also inside c, then I would just take those same values along the curve, put in z minus 2, and then take the Riemann sum and the limit, and it will tell me exactly what f of 2 is. Alright, so analytic functions, once you know what happens on the boundary, in theory, you know everything that happens in the inside as well. Alright, now let's go back to the practical side of things. Let's evaluate an integral. The integral we want to evaluate is cosine of z over z plus 1. Now, if you were to try and parameterize this and turn it into a couple of real integrals, you'll be hopelessly stuck. This is an integral that we definitely cannot do when the variable is a real variable. You may recall similar integrals that your calculus teacher may have shown you to tell you that you don't know everything once you go through second semester calculus. We're going to evaluate this function along the contour C, where C is the circle with center minus 1 and radius 1/2. Now to start off, what we're going to do is take a look at where the function is analytic. Now the fraction as a whole has a singularity at z equals -1. That's a point where the function is not analytic, and you can see why that is. You can tell that that point -1 is definitely enclosed by the contour C, and so we're kind of out of luck. The Cauchy-Goursat theorem doesn't apply here, and our rule for handling things of the form 1 over z minus z naught doesn't apply either, and the parameterization technique's not going to work either. Well, here's where the Cauchy integral formula becomes very useful. What we'll do is take a look at just the numerator, cosine of z. We're going to think of that as the function f of z inside of our Cauchy integral formula. And instead of z plus 1, we'll imagine that this is z minus -1. And so then using the Cauchy integral formula, we know that this integral, f of z over z minus z naught, should be equal to 2 pi I times the cosine of -1. Alright, and that's it. That is the answer. That's the value of the integral. So there was really no integration involved. We just kind of applied the theorem, and that gives the answer right away. Let's take a look at a slightly more wordy example. So let's evaluate another integral. This time let's insert z plus 2 inside of our integrand, and we'll leave c as the same thing it was. Now there are two ways you can do this. We'll start in both ways though by noticing that the fraction as a whole has singularities at -1 and -2. Now the point -1 is enclosed by the contour C, the point at -2 is not, and that will be important in a second, as you can imagine. Now as we go along, if we were to do what we've been doing the last few days, we might consider breaking this up into partial fractions. 1 over z plus 1 times z plus 2 can be broken up as 1 over z plus 1 minus 1 over z plus 2. And so we could break the integrand up in that way. We could say that this integral can be handled using the Cauchy integral formula in the way that we just saw. It's the same integral. And this integral, on the other hand, has a function that is analytic on the inside and on the contour C. Remember, the singularity here at -2 lies outside of C, and so by the Cauchy-Goursat theorem, this integral has a value of 0, and so we'll get our answer. Now, another way of doing it, though, is to use the Cauchy integral formula in a bit more clever of a way. I see a z plus 1 and a z plus 2 down below. I know that the z plus 1 corresponds to a singularity I need to worry about, but the z plus 2 does not, and so what I'm actually going to do is just move that z plus 2 up top. I'm still going to divide the cosine by it, but I'm just going to rewrite it in this way. Now with that in mind, I can take the whole numerator as my function f, again z minus z naught corresponding to z plus 1. So the Cauchy integral formula with this as my function f tells me that the value of the integral should be 2 pi I times the cosine of minus 1 times minus 1 plus 2. Now as you simplify that, you'll see that the answer we get on the right is the same as the answer we get on the left. So these are some tricks you can use as you apply the Cauchy integral formula to evaluate integrals. And you'll get a lot of practice on that in class and on the homework. Now, moving along, the Cauchy integral formula has sort of a generalization of some kind. We're going to separate it as a different theorem. We're going to call it Cauchy's integral formula for derivatives. It says simply that if f is analytic in a simply connected domain D, and that C is any simple closed contour inside of D, and if Z0 is any point inside of C, so the same hypothesis as before, then the nth derivative of f at Z0 is equal to n factorial divided by 2 pi I times the integral along C of f of z divided by z minus Z0 raised to the n plus 1. Now this will look very familiar to the Cauchy integral formula. And actually, if you consider the function f as the quote-unquote zeroth derivative, and you plug 0 in for the n's, you'll see that if we interpret 0 factorial as 1, then we get exactly the Cauchy integral formula from before. But if we were to talk about the second or the third derivative, this formula would tell us a lot of information, be useful. Now, in the same way that the Cauchy integral formula was useful both practically and theoretically, this formula for derivatives will be as well. So because we have an integrand here with a higher exponent on the z minus Z0 factor, if you are ever asked to integrate an expression with a high power factor in the denominator, you might use this, and your problem will just reduce to taking a derivative of what's in the numerator and evaluating that and timesing by 2 pi and dividing by n factorial. So you'll get some practice with that in class and in the homework. Now conceptually, what this theorem says is that if f satisfies the hypotheses, then actually f has a derivative, an nth derivative. Here's how we know. We know it has an nth derivative because we can say what a formula for it is. Now this is true no matter what n is, and so f will have derivatives of every order. And each of these functions are going to be analytic as well because they're going to have derivatives of all orders and so on. All right, so that's kind of an important conceptual result of the Cauchy's integral formula for derivatives. Now the consequences just keep coming along. As the section in your text indicates, we can also derive results called Cauchy's inequality, Louisville's theorem, the fundamental theorem of algebra, which is one you've run into before in your algebra classes, Morera's theorem, and the maximum modulus theorem. Now I'm going to ask that you be able to prove the first 4 of these. Each of these has a proof that is really not all that long. It's based on the Cauchy integral formula, and hopefully that won't be too bad. We'll talk about them as we go through class. But it all sort of ties back to the Cauchy integral formula. It's a great theorem. It's going to be very important as we continue into the future in the class. And I hope you enjoyed it. Let me know if you have any questions, and I'll see you in class.